Good afternoon, everybody. Today, we're going to talk about problem number 2 of USACO 2022 US Open contest Platinum level. This is a problem hoof and brain. It is actually a much easier problem compared with problem number 1. So the problem is like this. You basically have a graph, unidirectional graph. Then you have two persons, brain and the hoof. Every time when you make a move, brain can decide. You put two things on the graph, two tokens on the graph. Brain in every move, brain can decide which token should be moved, and the hoof can decide where it will go. If a token is picked that the hoof cannot make a move, then brain wins. Otherwise, hoof wins. So let's look at this example here first. So we have, in this example, we have a graph, which is from 1, I go to 2, 2, I can go to 3, 3, I can go to 4, 4 go to 7, okay, and then 3 can go to 5, and 1 also go to 6, 6 go to 8, 8 go to 9, 9 go to 6, which forms a loop, and then 7 goes to 2, which forms a loop. So, for example, if I study this case and this case, right? The first case is I have 1 here and I have 1 here. So obviously, in this case, if I have here, if I'm brain, I'll just pick this one, right? And then hoof has nowhere to go because it's unidirectional. So brain wins in first case. In second case, 1 and 2. If brain picks 1, and hoof can only go here, okay, then brain can, if pick 1, then just continue go. If you continue to pick 1, right, then hoof can continue go along this circle. So now we can see if there's a circle, seems like hoof can win, right? So if brain pick 2 here, then hoof can go here, and if you pick it, of course, hoof don't want to go here, right? Because then you got stuck, then you lose. Then go here. Okay, so obviously, if at any stage when brain pick 1, hoof will make it go this way, right? Because it can form a circle. If you pick 2, it goes this circle. So obviously, hoof will win. In the third case, 1, 6, just flip of that, right? 6 goes this circle, 1 will go this circle. So hoof will win. The other case, 2 and 4, this is interesting. So if I pick 2 and 4, if brain picks 2, then hoof will go here, right? Then brain can pick 2 again. Then hoof has no choice but go here, then you lose. If brain pick this one, it go here, pick 1 again, go. So even you have a circle, if you have 2 things on a circle, then brain will win because this one will get stuck, right? Eventually get stuck. So now seems like we have a couple of cases. Case 1 is if you cannot move, if there's a node, there is, outbound, number of outbound equals 0, that means brain will win, right? Like this case. In fact, if the number of outbound is 0, you can actually, if, for example, if I have a case like this, okay? So obviously this case brain will win, right? So if it's parents, so this is I, right? This is I, this is a parent of I. If parent of I only have, let's say, one edge, and its parent is its child, brain wins. That means in this case brain also win, right? So you can have this. So if you have a node, let's say you have a bunch of things. If brain will win at this node, I'm just going to remove this node from this adjacent matrix, right? If I get to the case, every time I move this node away, the adjacent matrix is empty. I mean, this one is basically, what this means is my adjacent, my ADJ list, right, is empty, right? So if I remove those from here, that means his adjacent list is also empty, right? So I can do a kind of like a reversed backfill, right? So I put in the queue, I set a queue of, I put in the queue every node that is the my ADJ list is empty, right? Then I propagate out. So this is the case. Okay. So obviously, what I will do first is remove all of those from my tree, from my graph. Then my second case, what's my second case? My second case is, if I look at this again, right? If I have a node like this, which has only one node going down, okay? So then go there, you have a bunch of things, okay? Then here I have a bunch of things, okay? So if this, right? If you only have one single edge going out, this node and this node actually is you can imagine it's the same node, right? Because if you're here, and if brain pick this, the only way you can go is here. So I can actually merge them together. What do we do for merge? It's union find, right? That's we know how to do this easily, union find. So I can simplify the graph by, if any node, right? So let's say this node is V. If my ADJ list of V, its size, equal 1, right? If size equal 1, okay, then I will basically merge those two together, basically using union find. Then what do I do? So this one, what do I do with all those coming in? For example, this has a couple of things coming in, this has a couple of things coming in. I will merge them together, right? So basically, let's say this is my super node. I will merge all those nodes together. Remember, when we merge two lists together, we need to do big to small, right? In order to contain, in order to maintain the log n complexity, right? Okay, so if you don't remember what that is, again, go to Benjamin Chee's USACO guide. Okay, I remember it's Platon level. It was small to large merge. Okay. So it's basically if you have two lists. Okay. Maybe I can find right here, right? So if you have two lists, okay, one is A, one is B. So you basically you want to keep the B, right? So if size A is less than size B, then you swap A and B. So A is the big one, right? Make A the big one. Then for everything in B, which is a small one, you insert the B into A. Okay, so swap is all one time, right? The merge is M is the small one, log M, right? Basically, your log is a big one. Okay, so that's how you improve the runtime. Okay, so use this small to large merge. I call it big to small. It's the same thing. Basically, you keep big in the log n, right? Because when you do an insert, it's log of this, right? You insert the small one. Okay, I should draw this one. Insert small one into it, so you have m of log n, right? So once you merged all those nodes together, so for example, if you think about example here, right? So this node and this node are merged together. Right? This become a super node. This remember I will remove it, right? Because it's a dead node as step one. And then this become big node, right? And this, so the whole thing become one big node. Okay, so then if in my last case, right, 2 and 4, if I picked this one and this one, they're all in the same node, that means brain will win, right? So same as here, right? So all this become one big node, right? So this cannot become because this has two outs, right? So basically, you basically become what it become. It become one and a big node. You know, let's say call it 2 prime, and the one big node, call it, let's say call it 6 prime. So if you know 1 5 is one is here, one is here, right? I mean 1 5 5 is dead. So 1 2 is one is here, one is here. So they are not on the same node. So that means Hoof will win. 1 6, one's here, one's here. Basically, Hoof will win. If 1 4, they're all in this big super node, right? So that was brain will win. So basically, what this is your check is like this. Your check is like this. If you belong to the dead node, right? If any one of them is dead node, in this case, right? That means brain will win. Okay. If they're all in the same supernode, if any of them is that node, right? If in this supernode, how do you find supernode? That's unified, right? Unified. If in the supernode, then B will win. Otherwise, H will win, right? So that's it. All this search, right? All this search is O1, right? Because, okay. I mean, all log and unified. So that is basically the problem. So basically step number one, you find every node that has output of 0, out edge is 0, those are the dead node. You put those into the queue, and then you look for them. Every time you find it, you remove this by meaning reduce this node from the adjacent list of its parents, right? Then of course, then you put the parents into a queue to search, right? You put the parents into the queue to search whether whether that parent is satisfied or not, right? At the end of the queue, right? So then you do this. Basically, you clean up the graph by removing all those dead nodes. I mean, mark it. You have to save it somewhere. You make those. You put a list, right? Basically, dead. You assign dead of v equal 1, right? If it's a dead node, that's how you mark it. Then after you do that, then you basically do this union find, right? So if this node's outer edge is only 1, then you can merge those together but do union those. Then for the incoming node of this, you merge into 1 by doing the small to large merge, right? So that reduces your complexity using this. Basically, it's just 2 lines of code. Then you do the check. When you do the check is if any node belongs to the dead node, the dead node is either this case or this case, right? Which I marked, or it's has the same parent in the union find. So that's H, that's brain. Otherwise, sorry, not H, that's B, that's brain, right? Otherwise, that's H. This is actually pretty easy problem to solve. Frankly, I would say it's one of the easiest problems we see recently in USACO class, in the USACO Platinum level. So hopefully you actually solve this problem. I actually don't think you need 4 seconds to get this done. So that's the class for today. Your homework is implement this. It should be pretty straightforward, probably 30 minutes to implement this code. Then next week, we will talk about problem number 3, up and down subsequence, which is actually also not so difficult. It's very similar. It's basically a twist of LIS, longest subsequent string issue. And we'll talk about that next week. And then the week after, we will start the review of the ROI problems. So please start to read the 2021 IOI problems. So and take some time to try to study and see whether you can solve how many of those 6 problems in ROI day 1 and day 2 you can solve. Okay, so that's a homework. Solve the Hoof brain and also look at the IOI problem. I'll put the link of the IOI in the class homepage. Thank you. That's it for this week.